Now let us try to solve this differential equation. Now this is here what we have is Cauchy's linear differential equation. Now that is okay, so we can write this as x square. Now this is d square, right, into y minus, now you have 2m minus 1 into, that is constant, so you have x here and you have dy here, right? So first derivative plus this is m square plus n square, now into y, right? Okay, so this is equal to n square and x to the power of m, and this is a log x, right? Now we can rewrite this as x square, this is d square, minus 2m minus 1, right, into xd, right, plus this is m square plus n square, and this is multiplied by y is equal to n square and x to the power of m and log x, right? So further let us put let us put log x as z, or you have x as e to the power of z, right? So then you have xd as d1 and x square d square as d1 into d1 minus 1. Okay, let us substitute all those things which I have mentioned here. So that is d1 multiplied by d1 minus 1, right, and that is minus 2m minus 1 into d1, right, plus this is m square plus n square, right? So this is whole thing multiplied by y, and you have n square which is constant here, so n square is kept like that, and you have x as e to the power of z, right, to the power of m, and log x as z. Okay, let us try to simplify this. Okay, so simplifying everything, you get this as d1 square minus, this is 2 m1 d1, right, plus n square, right, plus n square, right, multiplied with y, and on the right hand side you will have n square z into e to the power of mz, right? So now this looks like an ordinary differential equation, and it is non-homogeneous, and also it is second order differential equation. Okay, now let us find the complementary function corresponding to this. Okay, so the auxiliary equation corresponding to this, if I write in terms of k, because m is already taken, so let me write that. and just try to simplify it. Okay, so this is k square, right, minus we have this 2mk, right, plus this is m square plus n square, right, so which is equal to 0. So we have the roots, because it is a quadratic equation, you will have the roots as k, which is m plus or minus I. Okay, so you got the roots. Now let us write the complementary function corresponding to that. So yc, now this will be in terms of z, so let us write that e to the power of m z. Okay, so multiply that, you have c1 cos, now you have n z here, right, so plus c2, this is sin nz, right, close the brackets. Now we have taken e to the power of z as x, so this becomes x to the power of m, right, so c1 now will have cos of n log x, because z is x. Likewise you have to write the same thing here, so this is n times log x, right, plus the brackets. So what we found is the complementary function. Let us find the particular integral for this. Okay, so yp is equal to, you have e to the power of mz, right, and n square also you have that, okay, and z is also there in the numerator. That divides, this whole thing divides by, you have, this is d1 square minus 2m d1, right, plus m square. Let me write that clearly. So m square plus n square, right. Now let us substitute d1 as d1 plus m, right. This I have noticed that we have to take a as m, right, that's what we are substituting it. So let us take the constants outside. So constant is n square, and when we substitute d1 as d1 plus m, so we have to take e to the power of mz outside. So let us do the rest thing here. What we have is d1 plus m whole square minus 2m into this is d1 plus m, right, plus I have m square plus n square, right, so close the brackets. So what we have, only z is left here, and you multiply it. Now let us try to simplify this in the denominator. What we get that as this is n square, so this is e to the power of mz, right. Now when you try to simplify this, the denominator. So what we get after simplifying, right? So I get this as d1 square plus n square, so that is multiplied by z. So after simplifying this, I get this result. Okay, so this is, now if I take n square outside, so I can cancel n square, so I'll be left with e to the power of mz, right? And afterwards, if I bring it on to the numerator, so I get this would be d1 square divided by n square. So what I have done is I have taken n square and I have bring it on this on the numerator. So those two steps I have done, right? Let us further simplify, as well as I have cancelled out n square. So now let us expand this. So what do I get? So this is yp, which is equal to e to the power of mz, and this is multiplied by 1 minus this is d1 square divided by this is n square, right, plus this is d1 to the power of 4 and n power 4. So I don't require any other terms here because this goes to 0. So yp will be, that is e to the power of mz, and when you multiply this, so I get only z here and the rest terms goes to 0. So I can conclude this as z into e to the power of mz, right? Or I can write this z as log x. So, and finally I can write this as x to the power of m and log x, right? So this is your yp. So y is equal to yc plus yp. So hence we have solved this. Let us look into the next problem, right? Now what do we have here? Again, this is of Cauchy's linear differential equation. Okay, now let us write that. Okay, so we have this as x square d square into y, right, minus 2x d into y and plus 2y, right, is equal to x cube plus sine of log x, right? Now if I take y as outside, xd plus 2 into y, right? So this is equal to x cube plus sine of log x, right? Now let's put this as log x as z, right, or which is x is equal to e to the power of z, right, and xd as d1, right, and x square d square as d1 into d1 minus 1, right. Let us substitute that, d1 into d1 minus 1, right, minus 2 d1, and this is plus 2 into y. So this is equal to now x cube as e to the power of z, that is 3z, right, plus this will be sin z. And further, if I simplify it, I get this as d1 square minus this is 3d1, right, and plus 2 into y is e to the power of 3z plus sine z, right? Fine, seen this, right? Now let us try to we've got a normal differential equation, ordinary differential equation, which is of second order and it is non-homogeneous. Let us try to solve this complementary function and particular integral, right? Now the auxiliary equation corresponding to that would be, that is m square minus 3m, right, plus 2. Again, this is quadratic, you will have two roots, so the roots will be 1 and 2 if you look into that. Now the complementary function, which is yc, is c1. Now this is e to the power of z plus c2, right, and this is e to the power of 2z. Now this is c1x, right, and this is c2x square. That is yc now. Okay, we have finalized that in terms of x, y in terms of x, and let us find the particular integral, that is yp. That would be on the right hand side, what we had is e to the power of 3z, right, plus you had sine z that divides by, this is d1 square minus 3d1, right, plus 2. Fine. Now you got two particular integrals. Let us separately find that. So first let us find what is the particular integral, that is p1, okay, which is if I consider as e to the power of 3z divided by, this is d1 square minus 3d1 plus 2. Okay, let us try to solve this. Now I replace that d1 as 3, so this would be e to the power of 3z divided by, this is 3 square minus 3 into 3, right, plus 2. So these two get cancelled, so I get e to the power of 3z divided by 2. Or this p1 I can write that also as 1 by 2 x cube. So this is the first particular integral which I got. Let us try to solve another particular integral, that is p2. Here we have that as sine z divided by d1 square minus 3d1, right, plus 2. Now let us substitute that d1 square as minus 1 square, right. I'm going to substitute that, so I get sine z divided by this is minus 1 square minus 3d1 plus 2. Okay, further if I try to simplify this, so I get this as sine z divided by 1 minus 3 d1. Still we have to find, so let us multiply and divide by 1 plus 3 d1, right? So I multiply and divide by 1 plus 3 d1. Okay, so on that what do we have in the denominator? It is the numerator, what I had is 1 plus 3 d1, right? It is multiplied with sine z, right? And in the denominator this would be 1 minus 9 d1 square. Again let us put d1 square as minus 1 square, right? So in the denominator I'll have 1 by 10, right? And let us multiply that in the numerator, so I get sin z, right, plus the differentiation of sin becomes cos, so cos z. Now let us write in terms of x, so 1 by 10, and this is multiplied by sin z, which is of log x, right, plus this is 3 times cos of log x, close the brackets. So this is p2. Now y p will be p1, which we already found, which is 1 by 2 times that of x cube, and this is 1 by 10, and multiplied by sin of log x, right, plus I have 3 times of cos of log x, 8. So what we found is yp. So y is equal to yc plus yp. So this is the solution of the differential equation. Watch out for more videos which will be coming up right on your screen.